Write structural formulas for the two chair conformations of cis-1 tert-butyl 2-methyl cyclohexane. And are these two conformations equivalent? If something's equivalent, it means both of its conformations at axial and equatorial are equally stable. But here, after we drew one of our conformations, we realize that the other conformation must mean these branches are at an axial and an equatorial position. In order to do that, the cyclohexane we draw also has to be flipped around. So we can't just copy this lightning bolt. We have to flip it around like this so that it looks a little bit different. Or actually a better way to draw it would be like this, where the first corner is, the top corner is closer to the left, while here it's closer to the right, the bottom corner closer to the right. Okay, that's a better way to draw it. Okay, so this is our ring flip, and here we have our tert-butyl in up axial. So it's going to now be up but equatorial. Up, equatorial. And then the methyl, it is right now up, equatorial. We will make it up, axial. So what happened was when we flipped from the first cyclohexane to the second one, we went this way. We shifted everything this way. Boom. So likewise, if you were starting from this one, you would have to shift left to get to our other conformation. So now, are these two equivalent? No, because this one is more stable due to the heavier group in equatorial position. So the arrow is going to go right, and this is the result of a ring flip. So anytime they ask you to draw the branches in axial position to an equatorial position, instead of just moving these things to the equatorial or axial position, you actually have to move their positions as well. So move their positions and also flip the entire ring so that it kind of changes directions. So now which one's more stable? Like we said, this one's more stable, and it's also the one with less potential energy. The one that is less stable has more potential energy.